And we're back. Welcome back and happy Thursday. Today, we will switch gears a little bit and go over an introduction to a category of techniques for sense making, as it were, for data, an intro to machine learning. But before we begin, some administrative bits. The reading by the 4th of March, a week from today, in the text Learning from Data, pages 1 through 15, the PDF I have uploaded to the course Blackboard. There's also an accompanying video, should you choose to. The video is optional. There is the URL for it. So why don't we begin? Where we last left off, we talked about appearance-based features, and this consisted of a description of the color content in RGB color space associated with the image. And we computed that by isolating the red, green, and blue color channels and computing a test histogram over each one and concatenating those bin counts for the histogram as our features. We also can do the same thing with the edge map concerning the edge orientations as a descriptor of the shape of the content in the image. We concatenate together the vector for the color with the vector for the shape to form our appearance-based feature. And in this case, we had 10 bins in the histogram for RGB as well as for the edge orientation theta to form a 40 vector. So then we represent each image either as a point in some high-dimensional space or as a vector, which gives us the tools of vector algebra in order to determine how similar or how different from one another two images are. So let's take a look at what machine learning is. So let me ask you, if I say the word to learn, what does that mean to you? It might involve data. It might involve patterns. And machine learning, yes, does involve data and patterns, but really what we're after in machine learning is the mechanization of learning systems, crafting algorithms and programs that implement those algorithms that take data and uncover regularities in that data that you hope will apply well to brand new data. And so in machine learning, it's a branch of computer science, and computer science is divided into three parts: theory, the study of the algorithmic complexity and resources consumed by computation; systems, the engineering concerns with building those computational systems; and artificial intelligence, which traffics in processing of the data associated with computational systems. And so machine learning is a branch of artificial intelligence, and it straddles all parts. In the theoretical part that machine learning involves, we look at the difficulty of learning and whether learning is feasible. With the systems part, we're concerned about how you build learners. So we're concerned about the size of the data. We're concerned about the timeliness of the data and concerns such as those. And of course, on the artificial intelligence side, we're looking at techniques for how you characterize and uncover these regularities. But machine learning is a branch of AI, and we're concerned with the design and development of algorithms and the building of computing systems that modify their behaviors based on data. And so we find lots of examples of machine learning in the wild for dramatically different applications, but they share a lot of the same characteristics. Now, let's take the application above. We have web pages, and these web pages provide our data. They're semi-structured documents, and we compute or find a mathematical abstraction of this data, the internet graph in particular for web pages, where the nodes represent the content for the documents and the edges represent the hyperlink. And then we run some algorithm or statistics over this mathematical abstraction, and that arrives upon an application. In the case of web search, we have a relevance ranked list of search results. Let's take the example on the bottom. We have a car outfitted with sensors, things like radar, LiDAR, and cameras. And this gives us some streaming events. And from these events, we depict it as let's say an intensity surface, as we talked about with computer vision. And then we compute some statistics, convolution operator over that, and get the distribution of the edge orientations to measure shape. Now, of course, you might extract parallel lines or convergent lines to a vanishing point, and those are lane markers. You can extract that and use that for a control system to do something in an application such as lane keeping, making sure the autonomous vehicle stays in the center of its lane by maintaining a distance equidistant from the two lane lines to the left and to the right. And so here, while the application is dramatically different, these two systems, machine learning in the wild, have some of the same ingredients. We have data, we have some mathematical abstraction that we compute something over, and this results in an application. So let's look at what I like to call the anatomy of a learner. And these are the different parts of a learning system. And we're going to use a framing example for this, the credit approval problem. And let's imagine you're a large bank and you're trying to build a system, and it's going to decide whether or not an applicant should be extended credit. So somebody comes into the bank and fills out a loan application, enters in all sorts of information, such as the years in residence, annual salary, and a bunch of other pieces of data. Now, of course, we collect all of that data for each applicant, and collectively, each one of these descriptors or attributes defines that unique applicant. So we input that applicant's descriptors into the credit approval system, and out pops an answer: approval +1 or denial -1. Now, of course, there are reasons why you might want to and why you might not want to automate this process. Can anyone think of them? Well, it's federal law that if someone is denied credit, that upon request, the lending institution is required to furnish the reason why that person was denied credit. And so with such an automated system, it can say, well, if your annual salary were a little bit higher, you would have been approved. You can furnish those reasons, those explanations. That's a reason why you might want to use it. Now, the reason why you might not want to use it, well, the credit system, you might have somebody who looks like a bad credit risk on paper, but if you make the qualitative judgment, maybe he or she has lived in that area for generations, and their family's always known for satisfying their debt obligations. So there are reasons why you might or might not want to use such a system or automate such a system. And this just says that beyond technology, you have to decide when something requires human judgment and when you leave it to the system, and moreover, think about the impact of the systems that you're deploying. And so this is the anatomy of a learner. We can consist of a number of parts. We have an unknown target function, and this unknown target function is going to input vectors describing our customers, and it's going to output one of these results, one of these determinations: approval +1 or denial -1. And so floating out there is an ideal credit approval function, and we call that unknown target function. It's there working merrily along, but you don't know the bad news. You don't know what it is, and moreover, you have no control over it. But that function, it's talking to you. We have vectors associated with each customer: customer 1, customer 2, up to including customer big N. And each one of these vectors consists of all of the attributes that describe uniquely each customer from the historical data in the bank. Now, the good news is, while you don't know what the unknown target function is, it's telling you for each customer from our historical records for the bank whether or not somebody was a good risk or a bad risk. Were they approved or were they denied for credit? Now, of course, we have this historical data, and you have no control over both the unknown target function and the training examples. They're just there. If you know what this unknown target function is in closed form, that's not a scenario and not an application for machine learning. Just implement that function and be done with it. But we also have some components that you do have control over. We have a hypothesis set. And so this hypothesis set will be based on an educated guess, you select a candidate family of formulas that you believe would best describe what this unknown target function is doing. And we also have a learning algorithm, and that learning algorithm's job is to guide a search through the hypothesis set, looking for that hypothesis that most closely mimics the labeling action of this unknown target function. And that is your learned credit approval formula, and we call that the final best hypothesis, G. So G is going to approximate F, this unknown target function. Now, of course, the solution is found by search, and so we're searching so-called candidate hypotheses within the space of your hypothesis set that best approximates your target function. Now, some terminology, when we talk about the things that we do have control over, the combination of a hypothesis set, a candidate set of formulas, and the learning algorithm, we call that your learning model. And so we also include in this a distribution, probability P, that you have no control over, and this probability is responsible for the instantiations of the data that you get from training, as well as new data that you get outside of the training examples once you've deployed your system. You can think of this probability distribution as an importance weight, a score. Those examples or instantiations of customer descriptors, customer vectors, that are more important, they occur more frequently. And so associated with this probability distribution, of course, you don't know what it is. If you knew what it is, then you just implement it and sample from what you've implemented. We also have something you do have control over, an error measure. We talked about this idea that the learning algorithm searches through the space of hypotheses for that hypothesis that best approximates the labeling action of the unknown target function. Well, how do you determine what best approximates means? You have an error measure. And this error measure, in conjunction with the learning algorithm, as it searches through the space of hypotheses, is the criterion used to judge whether a particular working hypothesis over a series of rounds is the best hypothesis. Okay, so there are a number of learning models, and this is hardly exhaustive, but this is just representative that this idea of a learning model is this combination or choice of a hypothesis set and an algorithm used to search through that space of hypotheses. A neural network or deep network is nothing more than a linear combination of functions whose linear combination, weighted sum, is input into a function. And then the output of that function is composed through another linear combination that's weighted sum, that's input into yet another function. So it's just compositions of functions combined through linear combination is a neural network. Well, that's a certain category of hypothesis, type of functions, family of functions. Now, the algorithm for searching through the space of functions is called backpropagation. And what backpropagation does is it changes the weights for all of these linear combinations in proportion to the partial derivative of the error output from the network, that function, with respect to each one of those weight vectors. And it's called backpropagation. Take decision trees. It's a hierarchical decompositional model, and it's a particular type of function based on this notion of splitting your data into increasingly smaller, hopefully more and more homogeneous subsets based on testing whether or not certain feature instantiations are less than a certain value or greater than a certain value. And this decision tree is an interpretable model, and the algorithm we use to guide that search guides the choice of which split results in the most homogeneous subgrouping of all of your training inputs. And it's called gain ratio splitting, and it's based on entropy. And so here again, we have a choice of functions, and we have an algorithm to search through those functions. Bayesian networks is a graphical probabilistic model that encodes conditional independencies, and probabilities are a type of function. And belief propagation is the method you use to search by propagating or sending that conditional probability information through the network described by that Bayesian network. through that graphical model. And then we also have another one, latent variable Gaussian mixtures. It makes the assumption that some particular observed phenomenon is a weighted sum, a mixture of phenomena drawn from Gaussian distributions. It's a hierarchical model, and expectation maximization is how you search through those hierarchical models for the one that best fits your data. And so in each of these, while the function class is different and the search method is different, they are in fact learning models. Okay, so let's go through a simple example just to kind of frame how we represent our data. And so here in our ingredients for a learning system, we have our target function. And this unknown target function, as we said, it maps from the input vectors to our labels +1 for approval in the case of the credit approval problem, and -1 for denial. We have our historical data, our label instance pairs, consisting of a label assigned by the target function in conjunction with a particular vector instantiation for a customer. And then our final best hypothesis G that best approximates our known target function F also maps from the space of vector instantiations of customers to the labels +1 or -1. And so here we have a coordinate system. Along the horizontal axis, we have salary in tens and thousands. And along the vertical axis, we have years in residence in years. And so let's define a point, an individual who came into the bank, and this particular person, salary is, say, $70,000 a year, and years in residence is 7.5 years. We can have another customer record. This particular point represents somebody who makes $55,000 a year, and in years in residence of 10 years. And then likewise, we could have another person, $75,000 a year, and 15 years in residence. And so each one of these is vector valued, and each one of these vector valued quantities would be formed from the information that a customer fills in on their credit application that they submit to the bank. And so if you can have 3, you can have some number n of these customer records. And so you have your data set of size n. So here is a data set, and you note that some of these points are colored green and some are colored red. The green points are those for which the unknown target function has labeled +1, you're approved for a loan. And the red data points are those customers who have labels of -1, the so-called negative examples, labeled -1 by the unknown target function. They were denied a credit by the bank. And so this is called a point cloud. It kind of looks like a cloud, a point cloud in so-called feature space. And feature space is this coordinate system that represents each one of the vector instantiations corresponding to a customer is registered as a point in some multi-dimensional space called feature space. And so our entire data set, including our positive examples, the green points, the +1 approved customers, and the red points, the -1 denied customers, are drawn in feature space as a so-called point cloud. And so now the target function provides us with the ground truth labels in sample for those sample points we have from our historical data. And then the target function assigns these points into one of two groups: those people who have been approved, the positive examples, the green points, and those who have been denied, the negative examples, namely the red points. And so you can also think of the target function as partitioning these points into two groups, namely the red group and the green group. And so it's also known, this target function, as a decision boundary. It decides whether each point should be a positive point, approved, +1 label, or a negative point, denied, -1 label. And so you can select a family of functions, make an educated guess about your hypothesis set that you believe can best mimic this grouping of these points into these two groups, positive and negative examples, based on the data. And so we're going to hypothesize that, well, how to choose a line on the plane. And of course, going back to first principles, a line on the plane, f of x is mx plus b. And if we think about this line, it's defined in a unique line by two parameters, namely the slope and the y-intercept. And so if we say f of x is mx plus b, m is the slope, and b is the y-intercept. Okay? And so that means together, some selection for M and B, our slope and y-intercept, uniquely determines a line. And so I've depicted in the upper right-hand corner a hypothesis set that I call H subline. And so every choice of M and B is going to uniquely represent a line. And so let's choose an example line. This is a line of slope 1 and y-intercept of 5. So there's the line. And you can see that it gets a lot of these points wrong relative to the ground truth labeling by the unknown target function. Let's try this other line. This is a line with slope of negative 0.5 and a y-intercept of 15. That particular line perfectly coincides with the labeling of the unknown target function. So the green points are separated with one another, and the red points are separated with one another on one side of this decision boundary and the other side of this decision boundary. And you can also think of these positive points as being projected onto the positive side of the line, and the negative points, these red points, as being projected onto the negative side of the line. So if we were enterprising to search for the line that best mimics the target function, this is exactly what learning is. And you'd find that as we consider different lines or choices or instantiations of slope M and y-intercept B, as we're searching through our hypothesis H subline, we're going to traverse a twisty, turny, wandering path, searching for that final best hypothesis, the one that most closely mimics the labeling of these points by the unknown target function. And so the idea then is once our search terminates, we hope that the best line is going to work well with brand new data. And so if we have, for example, a new customer that walks into the bank, he or she fills out a credit application, we plot the vector for that new applicant that's not among the historical data, and then we ask the question, is this new customer red or green? Should he or she be approved or denied? And we measure by asking, well, which side of the line, that best line, does that new customer fall? And so essentially what we're enterprising to do is search for a line that works well with brand new data, this yellow point. And so essentially our criteria for assessing whether or not a final best hypothesis G is a good final best hypothesis is this idea of working well with brand new data, i.e., does it generalize well out of sample on data points or customer vector instantiations from this unknown probability that we have not yet seen out of sample. Okay. So what we need then is a number of ingredients. We need a data representation. We need a hypothesis set along with an algorithm to search that. We need a learning model. And then we also need a measure for how well we're doing, the error function, how we measure error in sample on those data points that we have from our historical data. And so that's what I'll stop with for today. And we will pick back up on Tuesday. As usual, please stay healthy, please stay safe, and I'll see you all on Tuesday.